Hi guys, this is Mr. Henson, just back with another little video tutorial on how to first of all describe, and second of all how to explain the data that we often find on our graphs. It's one of the hardest things sometimes when we come to science is to be able to do this, and it's one of the really necessary skills of any scientist is to be able to do this. So I've got a graph here. Now you'll probably recognize this graph. We've got temperature along the x-axis going up in increments of 10. So it's pretty much the same graph we saw yesterday from our other video tutorial. And then we've got rate of reaction, or ROR, in percent activity along the y. Now the rate of reaction is for an enzyme controlled reaction. The enzyme in fact is pepsin, which is a protease enzyme which works within our stomach and obviously breaks down proteins in our stomach. So first of all, let's try and describe the graph and what we're actually looking at here. So you can see here at 0 degrees Celsius, the rate of reaction of our enzyme in catalyzing the breakdown of our proteins is 0. Okay, then we've got, as temperature increases, we can see a trend whereby it's going up. Now you can see the line, the blue line here, it's going up slowly to start with. Okay, and then at higher temperatures, at between 30 and 40, it goes up to its optimum rate, okay, which is about, I don't know, 96% at 40 degrees. And then you can see above 40 degrees, it falls, and it falls very steeply, okay, denoted by the gradient here. This is a very steep gradient, look, much steeper than on the other side. Okay, then at high temperatures between 50 and 60, it begins to plateau out at 0% rate of reaction. And then above 60 degrees, it's 0 the whole way along. Okay, so what we've done there is we've done a basic description of what it shows us. Okay, so we've said that there's a slow increase in the rate of reaction at the start. Between 30 and 40, the rate of reaction rate increases. After 40 degrees, it comes tumbling down very quickly before leveling out at 60 degrees and onwards. Okay, so 0 rate of reaction there. So that's how we describe our data, all right? But that's not necessarily how we explain it. Now, for a conclusion, the job of a scientist is to really explain the data and see whether or not it matches your hypothesis. So first of all, let's try and explain what the graph is showing us. So at 0 degrees Celsius, you can imagine the particles in this having very little kinetic energy. Okay, that goes for both the protein that's being broken down and the enzyme. And so there is no collisions occurring between our two things. All right, so at 0 degrees, there's not going to be any activity because the particles are still. Okay, they haven't got enough energy to actually collide and for a reaction or a breakdown to happen. Now, as that temperature there, look, increases, okay, the kinetic energy is also increasing, okay, which means there's going to be more energy for our enzyme, more energy for our particles, and more collisions. Now, that's really important. So up here, we've got our optimum temperature. That means this is the temperature whereby you've got the enzyme and the food, or the protein, meeting at an optimum rate, and whereby the enzyme is still completely intact. It's not broken down. It's not being affected by the heat energy. It's just working at its best rate. Now we know at just above 40 degrees, as the temperature increases again and again and again, our rate of reaction comes tumbling down very quickly. All right. Now that is because we have our enzyme, which is essentially a type of protein. And our protein is essentially a string of amino acids. Now, as the temperature increases above 40 degrees, what's happening is the chemical makeup of your enzyme is being affected. The bonding in our amino acids is being affected. And we call this denaturing, okay? It's too much kinetic energy and it's being shaken until it no longer resembles the right enzyme. And so the active site of our enzyme does not fit the substrate, it does not fit the protein. Okay, and so that lock and key theory kind of goes completely out the window. The lock no longer fits the key, and the enzyme essentially has stopped working. Okay, and that's what's happening here. And you can see there's a very narrow range of the temperatures of which that happens. Between 40 and 60 degrees, it becomes completely denatured. Okay, now I hope that has helped. I hope that has helped explain some of the ways in which we can describe and explain data. Remember, first of all, describe and then explain. Try and include the data that you're using. Okay, make sure you use numbers, and that's really important. All right, I hope this has helped. Thank you for watching.